Okay, so welcome to Math 140, lecture number, what are we, 8? Math 140, lecture number 8. Today, the goal. What's up? Miguel? Miguel. Okay, today we have two goals. One is to finish chapter 5. And the other is to answer any questions that you have from previous chapters. Apparently, people have some questions. Now, I will say this. During office hours, as I was answering questions from a bunch of people, there was a lot of, oh, just use this formula. And there was a lot of, I don't remember that formula. Or I don't remember how to do that on a calculator. Or I don't know what language you're speaking and things like that. Your first job is to review everything. If you don't know the formulas, you're going to have a really hard time answering the questions. If you just jump into the homework without knowing the formulas, it's going to be very tough to, you read a question and it's like, how do I solve this? Your first attack should be, well, what do I have? What do I need? And what formula connects them? If you don't have your formulas, you're going to have a hard time making that connection. Jonathan, how are you? Can or won't? Got it. Okay. Okay. So, to that end, what questions do you have on chapters 1, 2, 3, 4, or the first half of chapter 5? I'll be more than happy to entertain questions right now for your viewing pleasure. Do you have a couple questions, Kermit? Go for it. Good job. Sure, I will answer a homework question or two. You want to read me a homework question? And then I will show you not only how to solve the homework question, but how to attack the homework question. In other words, as he's reading it, what do I do at various stages as if I was solving this problem myself? So go ahead, pick one, then you will have a question on, and I will do it right now.
Okay, I know you probably this one. It says the total scores on the medical college admission test follow a normal distribution.
Stop. Normal, okay, keep going.
With mean of 24.9.
Stop. Okay.
And the standard deviation of 6.2.
6.2. 6.2. And it's medical scores, you said?
Yeah.
So I will name this M for medical scores.
Okay.
Okay, so you've given me a sentence of information. I have encapsulated that information mathematically. Keep going.
What are the median and the first and third quartiles?
Stop. What is the median? We're looking for this. What is the first quartile? We're looking for this. What is the third quartile? We're looking for this. Okay.
The MCAT scores.
Okay. So I wrote down everything that was provided. I wrote down everything that I was asked to find. And now it's just a matter of making the connection between what I was given and what I was asked to find. So I look at this question and I say, oh, hey, this is a normal distribution. Okay, well, I know what a normal curve looks like. A normal curve looks like this, correct? Something like that. That's my normal curve for this problem. What's the mean? What's the center of this normal curve? 24.9. And what's the standard deviation? 6.2. So I'll do something like this, just to graphically be able to visualize the exact same information that I was provided. I've done nothing new in terms of solving the problem, but by making the picture, maybe I'll see something that I didn't see before. And right away, I see something. The median is the point at which half the data is to the left and half the data is to the right. Well, look at that graph. What's the value where half the data is to the left and half the data is to the right? 24.9, done. Maybe I didn't catch it in the first step, but I certainly see it when I made my picture. Now, what does it mean to be Q1? Well, this is not a 5-number summary. This is not a, one of those box and whisker plots, where you have something like this and it's like, oh, that's Q1 over there. This is the normal distribution. So I have to think a little deeper. What exactly does Q1 mean? It means 25% to the left. So maybe here's 50%. This would be, I don't know, maybe here somewhere. Maybe this is the point where this is 25%. And I'm looking for this guy right here. That's my Q1. Well, if only there was a way of determining which point on a normal curve has 25% area to the left. Do I have such a technique? Inverse norm. The inverse norm function on my calculator says area 25% to the left for a 24.9, 6.2 distribution. And when you plug it in, what do you get? You can't do this in your head. So what do you get in the calculator? What do you get? You're hitting buttons. I assume you're doing it. Yeah, oh, fine. Okay, dude.
To the left, right?
Yeah.
To the left.
Yes, this is like Rihanna to the left. Or Beyonce. I don't even know who it is. Who is it? Beyonce? It's all the same. You got what?
20.
I know. I'm sorry. Okay. Yeah.
20.72.
20.72. Okay, 20.72. Now, I'm not checking your work. I'm assuming you're doing it correct. If you come to me later and say, that was wrong, don't blame me. I'm just a messenger. But assuming he did it correctly, and when has Kermit ever been wrong?
He's right.
Okay, thank you, Ms. Biggie. Okay, so Q1 equals 20.72. So that's the first quartile. How do I find the third quartile? Now I have options. One way is the same thing. Just do 75% to the left, or 25% to the right. Gets me the same thing. Or I could just say, well, if I move to the left 4.18 from 24.9 to 20.72, just go to the right 4.18 because the normal curve is symmetric. So it's going to be 29.08. Is that what you get?
Yeah.
Did I get my math right? 29.08. And I have all of it. Does that make sense? I'm sorry? Inverse norm.
Inverse norm equals 25%.
Well, when you go to the inverse norm function, it says what's the area, what's the mean, and what's the deviation. 25% area, mean 24.9, deviation 6.2. The better calculator, the CE calculator, has the option of left. Sir, what's up? So left, right, or middle. So we're doing left. Well, I had a bunch of people coming late, so let's take a look. Let me just do that quickly. Emma, Steve, Alan, Angel, Nicholas, Christopher, or Sarah. So Sarah, I just came in. Angel. So Emma, Steve, Alan, Nicholas, Christopher. You are Christopher. Talk third person, guys. When you come in, when you say me, I don't know who I or me is. Yeah, that you I got. I know who you is. Okay. Does that make sense?
Yeah.
Again, most of this class, most of the mathematics will not be done by hands. Okay, this in particular cannot be done by hand. Even if you knew calculus and was actually able to calculate area under curves using the tools of calculus, this particular function can't be done by hands. So you have your calculator do it for you. Yes. Okay, good talk. Another question or no?
No.
All right. Did that make sense? Yes? See? Ken? Yes? Or different languages, see what's out there. Da. Da. Sprechen Sie Deutsch?
Ja, Paulus.
I just learned this yesterday. Just yesterday. I forgot how to say it though. Something in Polish, but I forgot what it was. All right, anyway. Yeah, so that's it. Questions? Yes,
This is to find the.
median, Q1, Q3. In reality, it's to find anything. If I said, what's the 40th percentile? Is it any different than doing it this way? The only difference is you don't put in 0.25. What do you put in? 0.4. From a calculator perspective, it's the same exact problem. Yeah.
So if you were to do the 5 to the left, put 1.5, this to the right, put 0.75.
If, I mean, I don't know why you want to find it twice. One way gives you the answer. Why do it twice?
Find Q1.
Find Q1, you do 25% to the left. Find Q3, you do 25% to the right. Or 75% to the left. You're finding different things. Yes? Yes? Questions?
Professor?
Yes.
So when you give the example, when you want to find for the 40th percentile on the tail, where I put, do I still put?
Area 0.4.
No, but for the tail. Do I just?
Area 0.4.
No, he has a smarter calculator.
I like
so-
the left.
Area 0.4. I have the same one you do. Area 0.4.
No, but I'm asking for the tail. Do you put left, center, or right? Or
Well, do you want 40% to the left or do you want 40% to the right? What are you asking
The
for?
question would tell me.
No, percentiles, you have to understand what they are. When I want the 40th percentile, where is that 40th, where is that 40%? To the left, right? If you're in the 40th percentile, that means you are better or higher than 40% of the data points, which means you have 40% to the left. Yes,
Why wouldn't you choose the center?
not until later in the course.
No.
Yeah, later in the course, when we're doing confidence intervals, then we're gonna say, you know, I want there to be 80% chance of catching something, and then you go off in the center and you want 80% to be in the middle. Well, we'll get to that later. Yeah, but now, you know, now it's just left or right. And some calculators only do left. The one I have does left, right, center, but some calculators only do left, then you gotta do a little more work. So let's do one just for fun. I mean, not an actual problem, just hypothetically. Suppose you didn't have a calculator that could do left or right. Suppose you only have a calculator that can do left. And I asked you what proportion are between this value here and that value there, whatever they are, you know, A and B. I don't care what they are. Here's your mu, there's some sigma. And I said, what proportion of your data falls between A and B, where A and B are specific numbers? And your calculator can't do from A to B. Doesn't have that option. My calculator does. A lot of your if you get the one I recommended, it does. But suppose you only have one that does left. How do you do from A to B if you only have a calculator that does to the left?
So you find the percent outside of the range and then just subtract it.
What do you mean? Be more specific, please.
Like, the percent to the left of A and to the right of B.
My calculator only does left. My hypothetical bad calculator that I have only does left. I can't do to the right of B. Yes. I can do left of anything.
Wait, what was your question?
Next. I said, if I only have a calculator that's to the left, how do I get between A and B?
Oh, yeah. Like the B.
And, okay, do all left of B, get that number, do left of A, get that number, and then subtract them. Cancel what's to the left, you subtract them, you get between. And if I wanted to the right of B, what would I do? I don't know numbers. Huh?
1 minus.
1 minus left of B. Because the total area under the curve has to be what? 1. That's one of the 2 conditions for being a density curve. Total area has to be 1. So if my calculator gives me to the left and says 72%, then to the right must be the other 28%. So these inferior calculators that you might have that can only do left, they work. It's just you must do a little more work. But you can still get it. Does that make sense? Okay. So With that being said, let's recap. If there's no other questions on 1, 2, 3, 4, or the first half of 5. Going once. Twice. Yes, 1 second, yes.
One of the homeworks was asking for like the percentile of an SAT score.
Great.
I did not-
Do you have a specific question in mind? Like right in front of you?
Yeah.
Amazing. How providential that you happen to have it there. Go ahead.
So
Read it to me word for word, please.
there are 2 major tests of readiness for college, the SAT and ACT and the SAT. ACT scores are rated on a scale from 1 to 36. And the distribution of the SAT scores. ACT is recent years has been roughly normal with a mean of 20.9 and a standard deviation of 4.8. SAT scores are reported on a scale from 400 to 1,600. 400 to 1,600. And then, a rough normal mean of 126.
126.
1,027.
I was gonna say, people are really dumb. Okay, 1026 and 209, okay? Okay, so as first, do we agree that other than the scales, which I happen to know are not important, I've encapsulated everything that you've said so far in these 2 lines?
Yeah.
Okay, keep going.
Reports on students.
Okay, 1 second, guys. I hear talking. It's hard for me to hear someone.
Tanya scores 1,278 on the SAT. What is her percentile?
Okay, so that's the only question? Huh?
Round to the whole number.
What's the percentile? Okay, well, it's a normal curve. What's the center? 1026. So where's 1278? To the right. We see that the sigma is 209, so it's a little past 1 sigma, maybe over there, 1278. And we want her percentile. We want what percent is to the left. How do I do that? Z-square is fine, you don't need to, but you can. But I can go directly in a calculator for this one. No, because we're going from, sorry. CDF, normal CDF is correct. I apologize. Normal CDF is correct. So how do I use normal CDF to do it?
Lower would be the 10.2.
No, lower would be
There.
negative infinity,
How do you add it to the calculator?
negative 999999999.
And they're like,
No, always, I don't know of it. There could be, I don't know. I just do negative with a bunch of nines.
You could just put 10 to the power of 99.
Negative 10 to the power of 99.
Yeah.
Yeah, as long as it's negative, a big number. And then what's your upper gonna be?
1278.
1278. What's your mean gonna be?
1026,
What's your sigma gonna be?
209.
209. And what does it give you?
0.88604.
0.886, 88.6%. Or 88.6 percentile. Does that seem reasonable? We're past 1 deviation up, right? We know that 68% is in the middle, 16% over there, it's about 84%. A little past it, yeah, it seems very reasonable. Now, was there a follow-up to that question?
That's it.
That was the
Yeah,
whole
that's, I think the, let's say the ACT ranges from 1 to 30.
Yeah,
So which,
so the question is, yeah, which ACT score is equivalence? In other words, had I taken the ACT, this is what I would have gotten. So how do you compare 2 normals?
What can you compare it with the Z-square?
I'm sorry?
What can you do with the Z-square?
100% you can. I don't even need to do that stuff. What I can say is the Z-score for the SAT, which is 1278 minus the mean divided by standard deviation, should be equal to the same Z-score when I apply it to the ACT and just solve for X. Their Z-scores are equal. So I said their Z-score formula is equal, only have one unknown. So now it's algebra time. Forget about algebra, now it's arithmetic time, yes.
Can you just do it first of all?
Or once you get 88.6 percentile, then I can say, what about having the other? What about having the other distribution, the ACT distribution, and figuring out what score corresponds to the 88.6 percentile? I can do this area to the left with this mean and this deviation, and what does it give me?
26.69.
26.7 approximately. So there's two ways of doing it. Either way works. This red doesn't really work very well. I like to throw it out, but I can't see the garbage can. That's not a challenge from there. No, I had like a sliver of it. I know I was a mistake. Yes.
Since inverse norm and CDF go hand in hand and are so useful, could we dismiss using Z-score?
Yes.
Okay.
Unless the question asks for the Z-score. Who's to know what you're gonna be asked to find? I can ask a question and test, find me the Z-score. I can do that. Z-score formula, data minus mean over sigma. Know your formulas. More important than anything else, know your formulas, yes.
What formula we use for the percentile?
I can't hear. Again, guys, small room. Masks make it hard to hear. I'm asking you not to talk. Yes.
Which formula we use for percentile? I will find it.
How to find the percentile or how to find the data points?
Yeah, the percentile.
In normal CDF. Normal CDF takes you to percents and inverse norm takes you back to data. You get both directions. So if I have my data, 1278, I'll do my normal CDF up until 1278, it'll give me the percent. It'll give me the percentile. And if I have the percentile and I want to go back to a data point, I use inverse norm. Right, one goes forward, one goes backwards. And every now and again, when I'm using the calculator, I accidentally go to the wrong one. I'm like, oh, wait, gotta use the other one. Takes me 2 seconds to correct myself, not a big deal. Anything else? Yes,
The Z-score formula is, what is it?
Data minus mean over
that's the one.
But data is just X.
Using X for the data point. Does that make sense? I hope. Okay. Who?
Okay, I was gonna ask, the reason why you said. Okay, I was gonna ask him, the reason why he said equal to each other was just to compare.
Yeah, how do you compare? How do you compare two distributions that are independent of each other? You turn them both into z-scores and then just compare their z-scores and see which z-score is bigger. Because remember what a z-score is, it's how many deviations you are from the mean. If I'm more than one deviation or more than this deviation from the mean in this distribution, I'd be in the same place in the other distribution, right? It's just easiest way to compare. Okay, so chapter 5. Still on chapter 5. The last chapter for the test. We will review all of next week. Both periods will be a review day. And I will use the workbook that I have posted on Canvas in class. We will just go through problems from there. Those questions are questions that were picked by the person in this course who was in charge of the final. So we know that the questions are going to be similar. So chapter 5, again, was on regression. Let's remember what regression was. You have in theory, it doesn't only have to be the first quadrant, but you have data points of some kind of distribution or some kind of scenario where you are determining whether there's some kind of correlation between whatever your horizontal coordinate is and your vertical coordinate, and you've decided, you believe that there's a linear correlation between them, and therefore you want to find the best fit line. How does one go about deciding that there's a linear correlation. You don't just look at it and say, yep, I see it, because your eyes can deceive you. So how do you determine when you have a scatter plot whether or not you think linear correlation is appropriate?
You find the least squares.
Now, before finding the least squares, you only find the least squares if you believe that it's linear. Otherwise, your least squares does nothing for you. How do I know? I want to know whether to get a least squares line. How do I determine whether or not it's appropriate for the given problem to regress it with a line like we did on the Tuesday?
You find R.
You find R. You find the correlation. Remember what R measures. R only measures one kind of correlation. What kind of correlation does R measure? Linear correlation. It can be perfectly correlated in a nonlinear way, and R will give you nothing. R provides linear correlation. So if my R is moderate to strong, and I decide, hey, yes, I believe there's some correlation here, some linear correlation, then I go ahead and I calculate my best fit line. I regress it. What does the best fit line do for me?
I have a question.
Okay,
The line, is it just y equals mx plus b, y hat, is it just a formula? It's not actually like, oh, right?
well, a line is always given by the equation y equals mx plus b.
Okay.
I mean, unless it's vertical line, but we're not going to have this. So there's a formula to it. There has to be, otherwise you don't have a line. Okay, good talk. So again, I don't even recall what my question was. It was, what's the point of the line? Thank you. Why do this? Oh yeah, that's really pretty. Yeah, that's a nice line. Why?
To measure the vertical distance,
To do what?
measure the vertical distance,
No, but thanks for playing. Someone else, yes.
find out the outliers.
No, but I like the idea, yes.
Find out what value, like predict the Y
To
value.
predict. It is a prediction line. If I come later and I say, oh, I have a new X value. I wonder what the Y value is going to be. Well, yeah, I don't know what the Y value is going to be, but I can certainly predict what the Y value is going to be by doing what? How do I? Well, looking at the line, or more specifically, plugging into the formula. When I have my Y hat equals mx plus b formula from, oh, what are the book? Yeah, I think the book does ax plus b or bx plus a or something. I don't even remember. But when you have your slope intercept formula line, if I come along later and I say, ooh, I have an x value a, and I'm curious what my y value for a is going to be, the best possible guess that I can make based upon the data that I have is that it falls on the line at that x value, and I can calculate that by plugging it in. This is why you never want to plug in an x value over here. Why do I not want to plug in an x value over there? Huh? Who's talking?
Because you won't get a reliable.
Why not?
Because it's outside of.
We came up with a great name of that. Yes, so we're extrapolating because it's outside of the domain of applicability, right? That's, I patented that. It's now copyrighted somewhere. Domain of applicability. This data point is way outside the range. Maybe once I get here, the data takes off in some new direction. I don't know. Maybe it does, maybe it doesn't. Maybe it's a wonderful prediction. I don't know. If you want to use it to predict out there in the world, you can do so. Might not be the best prediction. It's still a prediction. If I'm curious, for example, what the average height of a CSUN student is, or better yet, the average height of an American, and I go measure 1,000 people's heights, and I take the average of those thousands, is that a good prediction for what the average American height might be? 1,000 people is a pretty large sample, isn't it? I mean, it's listen, you ever make soup? You never made soup. You never made soup. Can you imagine somebody making soup? Now, if you make soup for yourself, a bowl of soup. Shut up, I'm talking now. You make soup, you make a bowl of soup, and you're curious, is the soup ready? What do? What can you do? You taste it, right? Ooh, it needs more salt, or whatever the case may be, right? Now, imagine you're a caterer, and you're making soup for 1,000 people, and you want to tell if it's ready. What do? Huh? One big pot of soup, one huge pot of soup. What do? You get a spoon. Do you get a huge spoon because it's so much bigger? No, it's same size spoon. Same size spoon. Who cares how big the population is? If the sample size is large enough and it's representative enough, I didn't only ask basketball players or jockeys or something like that, then 1,000 is plenty large enough to get a pretty good value for the average of all Americans. Is it going to be exact? No, unless I'm really lucky, but it should certainly be ballpark. But let's say I take 1,000 people and I pick the biggest of them, the tallest, and I say, that's going to be my guess for the average height of every American. Is that a good way of estimating?
No.
But it's a valid way of estimating. It's a perfectly valid technique. It's just a really bad one. Okay, I predict that the average value is 6'8". Okay, it's dumb. Why? Then you'd be even shorter than, what do you wish it's 6 foot? That makes no sense. I wish it was 5'1". Then I'm, never mind. Okay, anyways. The point is, I don't even remember what my point was. But I believe my point was something along the lines of that some predictions are good and some predictions are bad. Case by case basis to decide whether or not your prediction is good. So in this course though, if I give you a problem like this and I say, hey, here's my data point, predict, and you say, okay, I get this value. And then I come along with a follow-up question. And I say, was that a good prediction? Your value should be, no, you're extrapolating. Okay, don't do that. Don't be that guy or girl or anything. Does that make sense? So we have regression lines. We had a formula for them. Anyone recall the formula for the slope of the regression line? Oh, good try. It's like you have it there, but it's not quite there. No. Change in y over change in x is the generic formula for any slope. I'm looking for this slope, huh? R sy over sx. It's the correlation times the standard deviation of the y's divided by the standard deviation of the x's. You don't have to write that. You should have written that last time. And what is the y-intercept? Y bar minus mx bar. There were questions on the homework that essentially ask you to find the best fit line, not from the data, but from the data summary. These values, x bar, y bar, sx, sy, and r, those 5 quantities, all you need to come up with the best fit line. Where do those 5 numbers come from? Well, they come from the data, of course. But if you don't have the data and you just have those 5, it's good enough. So we did that last time. We also talked about last time, what makes this the best fit line? Out of all lines that I could draw, what makes this the best one? And we had this idea of calculating residuals, these deviations, for each data point, and doing what with all of those deviations? What do we do to them? Who remembers? No, nothing to do with standard deviations. These are deviations. We had all these deviations. Every data point had its own deviation. All of these have deviations.
They should equal 0.
No. You square them, you add them all up, and then do what? And then out of all possible lines in existence, you find the one that gives the smallest value for that quantity, which you don't do by hand. How do you get the answer to that question? Let your calculator do it for you. You do not do that by hand. Who came up with it? Yes, anyone know who came up with this idea? It was not Newton. It was not Sigmund Freud. It was not Turing. Long before Turing. After Newton, before Turing, it was Gauss. It was Gauss. It was Gauss, who was called the Prince of Mathematics, generally acknowledged as being the greatest mathematician of all time. He was pretty good. I did a talk on him when I was a student here. He did some really amazing stuff. Anywho, well, the discoverers of calculus are generally acknowledged to be Isaac Newton and Wilhelm Leibniz, who essentially discovered it at the same time in the 1700s. However, Archimedes already had worked out some of the ideas of calculus thousands of years earlier. And it wasn't until about 100 years after Newton and Leibniz, where you had Weierstrass and Cauchy and some of those guys who really put calculus on a very firm foundation mathematically. Newton was like, kind of like, oh yeah, you can just do this and get an answer. No. Leibniz was, what he did was fine. It's really a shame what happened to him. Isaac Newton was very secretive. And he discovered calculus, but he didn't tell anyone. And then Leibniz comes along and discovers calculus and tells everyone. So Newton says, oh, wait, guys, I knew it before him. I discovered it. And Leibniz is like, no, if you would have discovered, you would have published it. He goes, no, really, I did. And Leibniz is like, well, you know what I'm going to do? I am going to petition the Royal Academy of Sciences to set up an inquiry to determine who really discovered it first. And he did just that. He petitioned the Royal Academy of Sciences to set up an inquiry to see, was it him or Newton who came up with it first? There was one problem. Do you know who the head of the Royal Academy of Sciences was? Newton. So you can imagine the results of the inquiry. Luckily, history has come to the what we now believe to be the truth, is that they really did discover it so pretty much at the same time, huh?
Okay, so they said it wasn't, so the same time.
Yeah, Newton and Leibniz were contemporaries. Archimedes did some of the some aspects of calculus, thousands of years earlier. Well, calculus was completed long before Einstein, but Einstein definitely had contributions to a higher version of calculus. When you take calculus in college, you have calculus, then you have vector calculus, then you have the calculus of variations, and then you have something called tensor calculus, which is a fascinating field. And Einstein had major discoveries and contributions to tensor calculus. So it's beyond regular calculus by a significant margin. But he really did some amazing stuff. You might have heard of Einstein. You guys heard of Einstein? Yeah.
It's not like a lot of physics shit.
He did what?
He did a lot of like physics shit. Like,
He did one or two things in physics.
yes.
Yeah, one or two things. Not too much. Enough to win a Nobel Prize. 1905. He wrote 5 papers in 1905. Any one of those papers would have probably won him a Nobel Prize. And he did 5 papers. So that was a pretty good year for him. Huh?
Something about force and mass, nothing.
Nothing important. He basically proved everything Newton said was wrong. And to do that was pretty impressive stuff. Newton. All of Newton's laws of physics are wrong. If you're taking physics and you have Newton F equals ma and all that kind of stuff, yeah, it's all wrong. It's all wrong. Luckily, it's not so wrong, so that when NASA sends people to the moon, they still use it. It's just if you go far enough along to like the 10th, 11th, 12th decimal places, Newton's predictions and Einstein's predictions diverge, and Einstein ended up being correct.
Does it even matter though if it's that far off?
It matters from a theoretical perspective, maybe not a practical perspective, but GPS satellites or GPS in general, you would not have without Einstein at all. So it does matter. There's lots of things in math that people don't realize are important. Anyone know what an imaginary number is? You know, like 11 or something? So that was a joke, but everybody's laughing. Okay, let's move on. So imaginary numbers seem to be just that, imaginary. The square root of negative numbers, what can they possibly do for us? It turns out that you would not even have electricity or anything electrical if imaginary numbers do not exist. So, of course, I can't explain why, especially not right now. But a lot of the things that we take for granted or think are silly, or why do we have to know that? Or, you know, why learn this? Just be thankful somebody did. Like this class, everything we're learning, all statistics. Without it, kiss the FDA goodbye, and basically any medicinal study that puts cures of diseases at your reach, without statistics, you don't have any of that. So you might not care, but be thankful somebody historically did. Anyways, enough of my little diatribe, but I'd like an MB for that one if you can. Thank you. Okay, so let's go forward and let's talk about some facts about least squares lines. Facts about least square lines. There are things to know about least square lines besides the obvious. One I already mentioned last time, that if you switch X and Y, everything changes. And I say that hyperbolically, everything changes. We know the correlation does not change, but the slope changes, the y-intercept changes, what you're predicting changes. Okay, don't switch X and Y.
Professor, why would we do that? Like,
Why would you switch them?
Yeah.
I don't know. Sometimes, you know, if I, you know, one of the homework questions was to regress husband's heights versus women's heights. Let's say you want to do women's versus men's.
Oh,
It's a completely different question, right? Don't just randomly switch them. You get a completely different answer. Okay. Two, we already know this. I think it's a little obvious, but we'll say it anyways. The slope and R have the same sign. If the correlation is positive, the line goes up, and therefore the slope is positive. If the correlation is negative, the line goes down, and therefore the correlation is negative. They have the same slope. Of course, this makes perfect sense because remember R equals SY over SX. Sorry, M equals R times SY over SX. And these are positive. Standard deviations have to be positive, right? They're how far you go from the mean to the inflection point. So these are positive, which means if this is positive, so is that. If this is negative, so is that. Right? They go hand in hand. What else we got? There's one point. There's one point that always falls on every least squares line. And that is the point with coordinates X bar, Y bar. One way to help graph the line, if you have a question about graphing a least squares line, is that X bar, Y bar has to be on it. So if you calculate the average of the X's and you calculate the average of the Y's, and you make a point for those two numbers, that point must fall on the line. So if I have my theta points, whatever it is, and I've calculated X bar to be right here, that's the average of the X's, and I've calculated a Y bar to be here, the average of the Y's, then I know that the line, whatever it is, must go through that point. Doesn't have to determine the exact line, but at least I know that that line has to be on it. So it helps me narrow down the choices for what the best fit line might be. And last time, the last one, I'll say it again, it's this important, but last class, We talked about a lot at the end about R squared. We know R is the correlation. And R squared is the correlation squared. First of all, R itself has to be between what two numbers? This is back from chapter 4. What two numbers must R be between?
-1 and 1.
-1 and 1. 1, perfect linear correlation positively. -1, perfect linear correlation negatively. R squared, therefore, has to be between what two numbers? 0 and 1. Because if R was 0, R squared is 0. And whether R is positive or negative, when you square it, it becomes positive. And it can't be bigger than 1 because R can't be bigger than 1. So R squared is stuck between 0 and 1. And what does R squared give us? What is the physical interpretation of R squared?
It says how effective used by the data.
I'm sorry?
How effective used by the data.
Not exactly. What's that? Sorry. I had it, so yeah. Still not exactly. I'm hearing words that I said, but not exactly. Yes.
How much of the data that you actually put on will like cause the correlation? So like if you have a different set of data. I'm not.
0 for 3. Your hand was up. 0 for 4. I'm going to call it. 0 for 4. Yes. Oh, you're just reading it. You're just reading it.
That's reviewing. It's
Okay.
See the strength of the correlation.
I could have gotten that from R. I could have gotten that from R. Okay, so this is great. It's like playing telephone. You know, you say something and you kind of remember a few bits and pieces, but you're kind of forgetting all of it. When you have a scatter plot, like this one, are all the Y values across the entire scatter plot the same? No, the Y value is different, correct? Why are the Y values different? There's two reasons. One, well, the X values are differing. If I think there's a connection between X and Y, it does not seem reasonable that as I change X, the Y's are going to change. It certainly seems reasonable, correct? But sometimes I might have a single X, and that single X might have multiple Y values associated with it. Which means obviously X is not the only reason why the Y values change.
What percent of variation of Y is explained by the variation of X?
It's like perfect. Like whoever said that the first time, genius. So the reason why the Y values change across the scatter plot is twofold. One, the X values are changing. But even if the X value is the same, doesn't automatically mean the Y values will be the same. So there must be other factors out there that we're not considering. For example, if I was measuring heights of children versus age, and I have 10 babies come in, they're all exactly 10 days old. Are they all going to have the same height? Most likely not. What are reasons other than age as to why a baby would have a certain height? Genetics, right? Genetics, what the baby's eaten the last 10 days? I don't know. I mean, I assume nutrition kind of helps babies grow. I assume this is the case. Who knows? So R squared measures what percent of the variation in the Y values is explained by the variation in the X values versus what is explained by all those other things that we're not considering. So if I have an R squared value of 0.8, 80% of the reason why the Y values change can be explained by the variance in the X values. Whereas 20% are the things that I'm not considering. So what would I then do if I was really, really motivated in this study? I think I would try to eliminate those other factors if possible, and then try to see what the connection would be. Well, if this is a factor, then remove that factor. Hopefully, I'll have a tighter correlation. Oh, now I have that factor. Let's remove that. Hopefully, I'll have a tighter correlation. If I could ever get to an R equals 1, then I know I've removed everything. Or at least I think I've removed everything other than the one that matters. Does that make sense? This is where you nod and lie and say, yes, I got it. Yes.
Can you repeat your genius?
What did I say last time? It was really good.
What percentage of variation of y is explained by the variation of x?
Yeah, that's it. That's the one. Huh? Someone did. Someone certainly did. I understand. What you said makes perfect sense. But no, but this is really the key, is that you remember kinda. Kinda, like I don't know how to say it, but I kind of remember it. But when you're put on the spots, you realize you don't have it. Right? I didn't really learn, just, myself, I didn't learn calculus until I had to teach it. I had a master's in mathematics. I was teaching the stuff and people were asking me questions and I was like, yeah, I never really thought about that. Thinking to myself, oh, I never really thought about that. That's a great question. And all these little nuances kept popping up and I realized how much I didn't know and I really got a deeper understanding of it. So the Talmud says, anyone know what the Talmud is? The Jewish code of law. It says a person learns from his teachers, learns more from his colleagues, but learns most from his students. Not mistakes, we don't make mistakes. From his, no, I'm kidding. From his students. Everyone learns from their mistakes, but we learn from our teachers, we learn more from our colleagues, we learn most from our students. When you ask questions, and sometimes I'm like, oh, I never really thought about that. That's when the real learning comes in. Yes.
R squared, is that like the correlation?
Squared.
coefficient or something?
R squared. R is the correlation. Take it, square it. Now you have R squared. Sorry?
It has a name.
I think it's called like the coefficient of determination or something like that. I don't know. Is that what it's called? The coefficient of determination? Let's see. I just call it R squared. Does it have a name here? Yeah, even the book doesn't call it anything. I think I've seen it called the coefficient of determination, but I'm not promising.
Or is,
I just call it R squared, huh?
no, what is more
R is the correlation.
correlation?
Well, that much I know. Now, in the book, there's a section on what are called residual plots. We are skipping that. So if you do read the book at home, you can skip any reference to residual plots. If I accidentally put a homework question on residual plots, let me know, I will remove it. But we are not doing residual plots. Yes,
How do you find all of it?
turn on your calculator, do the work. We do not do that by hand. The formula is complicated and just your calculator will do it for you. Yes.
Stupid question, but are you skipping it just because it's not going to be covered on the final, or?
I'm skipping it because I don't really believe it is necessary to understand anything else in the course and doesn't really illuminate anything that we've learned or will learn. So I personally disagree with the author and do not believe it should be taught at this level. It's applications and uses will not be highlighted here, so I'm skipping. Okay, you will, if you ever take a more advanced stats course, right now our homework questions say, you have something that's normal. Well, in real life, how do you know if it's normal? Well, you have to test the data to see if it's normal. And one of the ways of doing that are with residual plots. We are not going to be doing that this semester. So I'm just straight up skipping it. It's unimportant as far as I'm concerned, and we don't have to know it. But the next section, we do have to know. And that is the idea of an influential observation. Influential observations.
So plug the data into like your calculator.
Yep, always.
Will it tell you that it's normal or what it's?
Nope. 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 The calculator can only do what you tell it to do. It does not tell you, yeah, this data looks normal. If I make a residual plot or one of my other devices, I can then analyze it myself and say, okay, I believe it's normal. Well, yes and no. There is something in the calculator called the chi-square test, which we will do later in the course. Not in this context, but we will use the chi-square. The chi-squared method, among other things, there is something called a goodness of fit test, which we will cover, and in the last chapter, a goodness of fit test. It tells you how good your data fits a certain model. So I come along and I say, I believe my data is normal. I will perform a chi-squared test, a chi-squared goodness of fit test. You can even see it on your calculator. If you go to stats, test, not count, but test. So edit, count, test. If you go to test and you scroll way down, you should see chi-squared GOF on your calculator, chi-squared goodness of fit test. We will do that later in the course. Not like this, but we will use it. So I can take my data and I can say, this is my actual data. If it was really normal, this is the data that I would expect to have, and then run a chi-square test to compare my actual observations to what I expect to get, and then analyze my results of that test to determine whether they're close enough for me to claim that I have a normal test, a normal distribution.
Testing if it's normal.
No, you can do with anything.
I mean, it'll tell you if it's skewed, right, skewed left.
No, it'll just, you have to come along and say, I believe this is the model. I believe it's normal. I believe it's this. I believe it's that. Here's my data. Let's see what my chi-square test tells me.
Yeah.
The test either will say, yes, your model seems good, or no, your model seems bad. It will not say, but try this instead. Right? It doesn't do that. Yes. Yeah, that calculator might have, that's a chi-square graph.
So this is proving it's normal?
No, that's just a chi-square graph. You haven't actually done a test. That's just a picture of a chi-square graph.
Oh.
That's got nothing to do with this. That's just a picture of a chi-square graph. That's not normal, by the way. That's not normal. A normal looks like this.
Right,
A chi-squared looks like that.
so it's always skewed to the right.
Yes. Chi-squared and normals are different. We're, again, getting far afield, don't need to worry about that now. Skipping residual plots. But we are doing influential observations. So here's a scatter plot. And I want you to tell me, very straightforward scatter plot. If you were to do a best fit line for these three dots, what line approximately would you draw? Would that make sense? I mean, what line would make sense here? Yeah, it seems like something like this would be good, right? Maybe something like that, I don't know, approximately. Seems pretty good, right? Oh, wait, I'm so sorry. I forgot one data point, my bad. Sorry, guys, I forgot that one. So, sorry, my bad. So, yeah, okay. Sorry, try again. What will be the best fit line here? Well, now, I might draw something like that. That one observation completely changed the character of my scatter plot. It is a influential observation. Notice if I would move this dot here, my best fit line wouldn't change that much, right? This one was not an influential observation. So what is an influential observation? It's a point, a data point, whose absence or appearance would have a major effect on the character of my scatter plot. Those are not the, well, the words in the book are close. So after you write what I just said, I'll read for you the books word for word, and you can tell me whether or not I'm basically said the same thing. It says an observation is influential if removing it would markedly change the result of the calculations. Seems basically to be saying the same thing. Okay, that is an influential observation.
Can you read it one more time?
Theirs or mine?
Or yours?
Mine, a data point is influential if its absence or appearance markedly changes the character of the scatter plot. Pretty sure those were the exact words, which is crazy. Yes?
Markedly change the scatter plot or the line?
The character. In other words, I'm going from a positive to a negative, right? My original best fit line was positive, now it's negative. Everything about the scatter plot has changed. The data points are all the same except for the one, but the way I interpret the scatter plot is completely different because of that one observation. That would be an influential observation. And there's a paragraph here, very important. It says, the result of a statistical calculation may be of little practical use if it depends strongly on a few influential observations. So again, the result of a statistical calculation may be of little practical use if it depends on a few influential observations. This is why we want to have lots of observations. The more observations you have, the less likely it is that any of them are influential. Right? If I had 100 of data points, it's very unlikely that the removal of any one of them would markedly change the character of the scatter plot and therefore would not be influential. Does that make sense?
We have a question.
Yeah.
Why do we just write that?
Oh, we wrote it because I think it's important to write.
Yeah, but like, what does it connect to? What did you talk previously? I was writing the other part, where you said data points whose absence has a major effect on the scatter plot.
Right, so a data point whose absence or appearance has a major effect on the scatter plot is influential. If you have a few influential observations using the scatter plot to actually predict things, it's probably not worth it. There's little, probably not worth it. There's little practical use in using a scatter plot that depends on some influential observations. So we don't like influential observations. We want to get rid of influential observations. This one here, influential. Oh, I'm sorry, let me throw in some more data points. Is it influential now? No. Okay, so the more data points you have, the less likely it is to have any influential observations. If you have influential observations, that's not a good thing. Because it means, what if those influential observations are outliers? What if they're not really of not importance? They're not the standard results. Then you're basing all your statistical analysis on anomalies. We don't want to do that. So in this course, most of this course is technique, solve problems, get results. But we're also trying to prepare you for the world. And the preparation in the world is, when am I allowed in the world to do all these techniques? And here's a caveat. If you have influential observations, don't use it. Yes?
What if it's not really an influential?
Then
What if it ends up being just an outlier? Can you test it?
well, in real life practice, certainly, anything that I think is an outlier, I'm going to want to check, was it really an outlier? 100%, right? But in a basic level of stats, we gotta build it up, right? We gotta give you the tools. Most of what we do, you can't just get out of this class, get a job in statistics and start doing research. Because there's lots of things that you're not going to know, and even the things that you learned in here, you're going to forget half of it. Right? That's just the way it is. Don't go out there thinking you're a master of stats just because you passed this course. I'm trying to give you some tools here, but be aware that in real life, even the basic theorems that we do, basic formulas, are all improved upon by more advanced ones that we just can't cover at this level. right? It's the same thing about the physics earlier. F equals ma. Yeah, it's wrong, but it works fine for a beginner. So that's what we're doing here. This is my F equals ma stuff. Everyone here knows it? F equals ma. You know a little physics? No physics? Well, now you do. There's no specific analog to F equals ma to be replaced with something else. The problem with F equals ma is it implies that a constant force creates a constant acceleration. Constant acceleration means the speed will continually increase forever. According to Einstein, nothing can go faster than the speed of light. How can you increase forever if there's a cap on your speed? Those two can't both be true at the same time. Which one's true? Well, Einstein's true, as far as we know. My father just this morning, read me a title of an article that he found online where they passed some other test. They did something again and showed that Einstein again was right about something else. It's just every single time they test his theories against something else, he's passed every one of them. Go Albert. Anyway, any questions on this? This takes us to the end of chapter 5. At this point, we have finished, we have completed everything for the first test. In, how many weeks has it been? 3 weeks? 4 weeks. Are we 4 weeks in already? Crazy. 4 weeks. Okay, which is about right. 5 chapters in 4 weeks is about right. Again, a little ahead of schedule. So the next 2 days of next week, Tuesday and Thursday, will be review days. Now, in the past, I have made the mistake of making review days optional. And you can come into class if you want to review, but if not, don't worry about it. It's only a review, nothing new. And then I show up to class and like 4 people show up. And then people take the test and everyone fails. So no, just because it's a review day, we still have mandatory attendance, lives along the lines of taking attendance. Again, there's no penalty for not being here other than not learning the material. There's just no reward of extra credit at the end of the semester if you miss too many classes. So I recommend being here Tuesday and Thursday. Does anyone here by a raise of hands think they are now a master of these first 5 chapters?
Absolutely not.
Okay, well then, if anyone feels they have somewhere better to be than here for a review session, I would love to talk with you and knock some sense into you. Now, as I mentioned before, every year, every semester, if you're teaching this class, at the end of the semester, the head of the department, not the department, but the head of the Math 140 subsection, gives us the results of all the Math 140 sections. And every year, I am among the top 2 or 3 classes in terms of passing rates and scores and how people do in the final. I do not want to be among the top 2 or 3. Where do I want to be? I want to be the top, which means you guys have to put me up there. Yes,
How many 140 classes are there in total?
there's a total of 19 sections that are not 140. I believe there's 5. No, there's it varies semester to semester, and I believe there's like 7 or 8 sections. Yeah, if it was like 3 and I'm always in the top 2 or 3, that wouldn't be so good. But I believe it's like 7 or 8. It varies semester to semester because attendance varies fall and spring and whatnot. But no, seriously, I want everyone to do well, and therefore I will give you 2 days of review. Yeah, any questions?
Is the test gonna be online?
Is the test going to be online? No, the test will be in person.
Oh, yeah. In person.
I'll be giving paper exams. It's hard for me to monitor everyone on their computer when you're facing that way. And screens are bright, so people can look at other screens and whatnot. I think paper is preferable. Yes.
Is it gonna be multiple choice, fill in the blanks?
So it'll be some multiple choice. it will be some short answer questions, some true or false, some wordles in there. That was a joke again. You guys gotta laugh more, really. No, it'll just be, I know for sure some true, some multiple choice. I don't do true or false a lot, but I have one question that I've asked in the past is true or false. Like, 10 questions, circle the true or falses. I don't really like them so much because you can guess and get them right, and I'm not really a big fan of giving points for no reason. I want you to earn your points, but there could be some of those. Could be some, circle the right option ones, like, one of these 5 yes.
How many questions are gonna be about?
Well, I can tell you how much I asked in the test that I gave last semester. Last semester was, I cannot minimize my Zoom while okay, hold on. Last semester, do I have it here? I don't even think I have the test from last semester anymore. I usually just toss them when I'm done with them. I don't like to reuse tests because tests go get around. But let's put it this way. Nobody came out of the test. Well, some people came out of the test saying the test was too long. And those people I'm watching because it was open book, open notes. And they spent half the test looking for formulas. If you do that, it'll probably be too long. Don't rely upon your notes. And we got to talk about that too, by the way. I think I mentioned on the first day that I have the option of making the test open book / open notes, but the final is neither. And that I can do whatever I want for the midterms. I can make them open book, open notes, and hey, great for you guys, but in the final, you're thrust into a new situation where you don't have that option. Or I can make the midterms like the final, so you're better prepared. So let's do we don't have the same option like we did last time. Who's a genius, by the way, who came up with that thing last time? That voting thing. Good call. We don't have that option here. So I'm gonna just do it simply and wait until I ask you to raise your hand. Who wants open book, open notes? Okay, let's try this again. I'm counting 2 hands is skewing the results, and I don't want that. 1 hand. I know you're trying to be funny with 2, but don't do it. 1 hand, high. I will do this when I want you to put your hand down so I can get an accurate count. Who wants open book, open notes? 1. No, Sarah, 1, 2, 2, 2. Thank you. 3, 4. Just please, why do I have to fight this every time? Why? I want to do it this way. Okay. 5, 6, 7, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, now who does not want open book, open notes?
What are the other options?
That's it. That's it. Okay, so it'll be open book, open notes. But I'm thinking the second test should not be open book, open notes. As we get closer to the final, it should be more like the final. And then also we'll see, how did the open book, open notes even help in the first place? Yes.
You won't really have to look, since online you can.
Open notes then. It's a good point. Yes.
We take our notes digitally, without.
I can't have computers open to the test. I can't have iPads. Anything with the Wi-Fi access, I can't have open to the test. Huh? How would I know if it's off or not? Guys, I'm not gonna walk around and check everyone's iPad to make sure it's off and then continually check it. Nothing electronic. Yes,
How many tests do we have? Because you said the closer and closer.
I think it's 2 and then the final.
Oh.
Maybe it's 3. I really don't remember. It's either 2 or 3. Yes. Call it what you want. It's a test. I don't care. Test, midterm, it's all the same. Yes. They're not cumulative, but that's what you're asking. Yes.
So when you're saying midterm, so this is gonna be 3 tests and then the final.
2 or 3 tests and then the final. Whatever's in the syllabus. I don't remember offhand. Yeah. Yes.
Which are like the pages of the book.
I don't know. Just nothing electronic. Print the whole thing if you want. right? I would say I would say anything you can carry in, you can use. But in the past, I have known people to carry in people. So I can't allow that. Papers, as many papers as you want to bring in. But again, I warn you, if you rely upon that to find things, the test will probably be too long. Okay, if you look at a question and say, oh, I know how to answer this, and you just answer it. Like, for example, when I sit down to take the test, and I do it, not from memory, but because I read the question, I think about how to find the answer, I find the answer, and I finish it, it takes me about 15 minutes to do the test. And you have 100 minutes. So I'm giving you roughly 6.5 times how long it takes me to do the test. That's how much time you have to do the test. 15 times 6 is 90. Now, if you don't know the formulas and you keep having to looking things up, or I say, is this an influential observation? You're like, what the hell is an influential observation? And you find in the book, that takes time. And that will add up, and you will probably not finish if you keep having to do that. So know the stuff. The notes should be there. If you forget, or if there's a formula that you know exactly where it is, you just don't want to memorize it, but it should not be, let me write down everything he said, so I have it all, and I'll use really small print, so I can fit it all on 2 sides of an 8 by 11 page, and you bring a magnifying glass to find things. In my experience, people who do that fail. Know the stuff. Yes,
On the final, do they give you like a formula sheet or?
there's a formula sheet. I'm not going to provide it here because you have your own notes.
Right, so we don't have
But-
to worry about memorizing every single formula?
Right, on the ones that do not have that will not be notes, I will provide a formula sheet. Doesn't have every formula, but it has the formulas that I will provide for you, and you will know in advance what they are. And the other things you will have to just know yourself. Okay? Questions? Yes.
Like you said, like yesterday, you said most stuff could be done, like in this class could be done on the calculator, but then there could be some formula that we would have to remember to do by hand.
Well, if I ask you to find the z-score,
or yeah, like that.
you need to do that by hand. Your calculator, you could plug it into the calculator, but your calculator doesn't know how to do it. There's no like z-score function where you plug in this, it gives you the z-score.
We're gonna have to show work.
Are you going to have to show work? If your calculator does the work for you, no. If it's something that I cannot do in my head, you would need to write it down. So my rule is that if I can't do it in my head, you can't do it in your head. Because even though I've only known you for 4 weeks, I am better at math than you are. A lot better. So if I cannot do it in my head, you can't do it in your head. So if I can't do something and you magically get the right answer, and it's not a calculator thing, then you will not get credit for it. In fact, it'll be worse. I will then ask to see the person's test next to you and compare them. Because if you can do it in your head and there's no work to demonstrate it, I will start to suspect. And just so you know, this side of me, this joking, fun side that likes to have a good time and joke and curse and make people laugh, if you get caught cheating on the test, you will see a side of me that you do not want to see. I take cheating personally, like you are attacking me. I will rip up the test in front of you. I will report it to the dean. I will try to get you expelled. Do not get caught cheating in my class. Cheat all you want, just don't get caught cheating. Okay, if you do, be prepared to pay the consequences. Okay, it's a different side of me. It's a Dr. Jekyll, Mr. Hyde situation. Do not make me go there. So if you have to think up, think down, do not think sideways. Don't do it. This is on YouTube, so if you're gonna watch this later, I can prove that I said this. You can't come later. You never said that you would get me expelled. I'm telling you now, do not let me catch you cheating. Okay? Is that clear? I want to nod. I want a nod. A nod, a nod, nod. Peter? Nod? This guy? Nod?
Then we could look up, right, if we're thinking.
You could think up.
Yes, okay, I do that, so.
So nod,
Yeah.
not acknowledge what I said, acknowledge. Acknowledge, 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 acknowledge. Current? You? Hey, yeah. Okay, you've all acknowledged. So no one can come later and say, I don't remember you saying that. Yes? Yes, it's a small room. It's a small room. I will try to get proctors from the math department, people who can be here to help monitor. Because I will be honest, when I was a student, I cheated. Okay? I was a good cheater. I did not get caught. It wasn't until much later in life that I became a teacher. And I actually went, believe it or not, 20 years later, I found some of my old teachers on Facebook and whatnot to apologize to them for, yes, actually, for how I behaved and what I did in their classes. Okay, I have changed in my old age. So please, hey, please do not make me go there. I'm asking you not to put me in that position. But if you do make me go there, just you've all acknowledged. Okay? So when we do have that test, I don't know how this room's gonna work out. I mean, temptation is there, even if you don't want to cheat, temptation is there. Sometimes it's hard not to look at the person next to you if you can't get something right. I don't know how I'm gonna arrange the room and, try to make columns and separate and whatnot. I'll do the best I can. But you all heard me say it, so I'm asking you again, don't make me go there, okay? Some of it is multiple choice, but